Hello, and welcome to the time series session of Virtual Mathematical Psychology 2021. My name is Konstantinos Sokratos, and I'm a first-year PhD student at the University of Florida. Today, I'll talk to you about the model of timing in simple anticipatory decisions. Additionally, reactive response times have been used as measures of latent cognitive processes. Subjects are instantaneously exposed to a set of stimuli and must respond once ready. Often speed is incentivized through time pressure tasks. And even though as humans we found ourselves in spontaneous situations where we have to make an instant decision or judgment, very often it is true that our everyday tasks tend to be more systematic and therefore somewhat anticipated. We tend to wake up, go to work, have lunch, dinner, drinks, usually around the same time every day. And for these anticipated tasks, individuals have to use readily available information to infer or project an outcome. For instance, what time should I leave the house if I want to be at work on time? Or if I have to meet friend X on a particular time, what time should I leave depending on the day and traffic so that I reach an anticipated event on time? We decided that we will create two different tasks, timing and representation, in an attempt to address the question of how participants make prospective decisions under different timing pressures and levels of uncertainty. In the first task, timing, we worked with response times. Subjects were instructed to press a start button to initiate the animation, and then they were instructed to click on a stop button once they thought the ball was going to reach the far end of the occlusion that you can see here. So if I were to do it, we'll start the video, they had a start button, and then the moment I thought it was going to hit the wall, I did it too late, sorry, you click on stop. In the second task, it is basically very similar to the first one, but this time they will have to wait for the entire video to play, and then at the end, a light will flash and ask them where is the ball. So in this task, we didn't work with response time, we work with location, coordinates, and here the participants had to click within the gray rectangle where they estimate that the ball will be depending on the ball's distance and speed at which it was traveling towards the wall. In the first task, we recruited 94 participants, but only 83 were retained. We coded the experiment in JavaScript code, and then we embedded the code into a Qualtrics survey. And we decided that we want to do 3 main manipulations at 2 levels each. So first we manipulated the distance. As you can see here, the ball will either start traveling from the middle of our screen towards the wall, and that will be the short distance, or it will either start traveling from the far left part of our screen towards the wall, and that will designate the long distance. Then we manipulated the width of the occlusion, and we had either a narrow wall or a wide wall. And then we lastly manipulated the speed at which the ball traveled towards the wall. It will either be fast or slow. This led to our 8 experimental conditions, where N or W will designate the narrow or wide occlusion, S or L will designate the short or long distance, and F or S will designate the fast or slow condition. To model such task, we decided to use the shifted Wald accumulator model. It is a single boundary 3-parameter accumulator model where the decision process is thought as a continuous uptake of noisy information. Basically an accumulation of evidence that stops once a decision threshold is reached, like here, at which point a decision is made and a response is initiated. The model has 3 parameters. The first one is the threshold, or alpha, and it is the boundary separation parameter. A high value of alpha means that more evidence needs to accrue before a decision can be made. And also large values of alpha reflect on conservative decision criteria, whereas small values of alpha reflect more liberal decision criteria. The second parameter is the drift rate, or gamma. And here it represents the quality of information provided by the stimulus. And it is basically the evidence accumulation rate towards the decision threshold alpha. Larger drift rates reflect an ambiguous stimuli, from information that's easy to process, resulting in quicker decisions, while smaller drift rates reflect ambiguous and complex stimuli, resulting in longer decision times. Finally, the last parameter is the non-decision time theta, time for non-decision processes. And here it is basically it reflects the encoding and response processes. And a larger value of theta will reflect to slower encoding and or execution, whereas small values of theta reflect to fast encoding and or execution. It is important to note that changes in gamma in the drift rate will affect the mass tail of the Wald distribution, while changes in the alpha parameter will affect the deviation around the mode and the normality of the distribution. And changes in theta, non-decision time, will determine the onset location of the Wald distribution. So the results of our first experiment, they were very, very positive. Here you can see the histogram of response times across each experimental condition. You can see the observed RT of the participants, and you can see that the vertical black line corresponds to the true heating time. The histograms of RT here show that our subjects recorded late responses in the anticipatory timing task far more frequently than they recorded early responses. In the majority of conditions, people were late in their timing estimates rather than early, which is really interesting. And also in the cases where subjects responded early, they tended to be only slightly early, whereas if they responded late, there was a much larger variance across conditions and subjects. This led to the highly right-skewed response time distribution that is shown here. And this reflects also everyday life examples, because people tend to be 5, 10, 15 minutes early, but when they are late, they can be anywhere late from 5 minutes to multiple hours. I'm sure we all can think of an example of someone we know. Here we have the highest density intervals in log scale, except for the grand mean, that is the exponent of the values that are shown here. The HDIs, as we already know, if both values are below or above 0, they then reflect on a reliable effect, while if they are crossing 0, then the effect is not reliable. And the good news is that for most of our conditions except one, the wide, the HDI did not cross 0. It only did for wide and variability, which could make us think that wide or narrow did not affect variability a lot. So the HDI represents the marginal increase when it is a positively signed interval, or the marginal decrease when it's a negatively signed interval for the level of the condition. For instance, the rate for the long versus short condition is negative for long, which means that the gamma or drift is lower for long compared to short on average. And as you can see here, fast is positive, which means that the gamma is higher for fast compared to short conditions. And then here is the model's goodness of fit. we ran two estimations. First, parameters were estimated independently for each condition. And then in the second estimation, they were estimated across conditions. Here you can only see the goodness of fit for the second model across conditions. Because parameterizations are transformations of each other, we get the same goodness of fit. So we only, I have only shared the goodness of fit of the second model. And as you can see, the wall model predicts the data excellently. The parameterizations represent the main effect of the three conditions marginalized over the other conditions. Like for instance, the effect of distance averaged over the occlusion width and speed factors and so on and so forth. So the shifted wall accumulator model does a great job at predicting response times. Which brings us to the second experiment. And as I said, what we gathered from the first task is that the wall model does its job excellently, and that is why it has been so widely used in predicting response time tasks. But how will the wall model perform when it comes to predicting location or coordinates? That was our main intention, to test the model in a different paradigm. And here we have the second task. We recruited 21 participants, and again, the JavaScript code was embedded into a Qualtrics survey. Same conditions as in the first experiment, but here we had a slight change. Each condition had 4 different endpoints. So for each condition, which, as I said, were identical to the previous task, narrow versus wide, short distance versus long, fast speed versus slow, we introduced 4 different stopping points once the ball was occluded behind the wall. So the first position was at about 20% of the occlusion, or 0.2. The second one was at about 40% of the occlusion, the third one at 60%, and the fourth one at 80% of the occlusion, which means the ball had more distance to travel between the 4 positions, leading to a longer time behind the occlusion for each condition. And here is the location model. We tried to tune different versions of the world model. The first one was with a no start bias, and there we assumed that the ball starts at exactly at location 0, thus no start bias, and expectation and uncertainty about its position grows linearly with time, so mean and variance. And that reflects the path of a diffusion process in the world model. The second version assumes there is a starting point bias, which is a function of participant and condition. So here you can see the model that the response is drawn from normal, and there is an intercept plus drift times ball position, diffusion squared times ball position. And when the intercept is set as 0, when it is fixed, it is the first model. Fitting hierarchically or not did not make any essential difference to the results. So the results of this experiment weren't as great as the first one. When it came to, Florida weather, when it came to the fixed model, it performed poorly across all conditions, but the free intercept model did very well on some conditions, such as NSF, or all right with others, such as WSF. And this made us think that as a next step, we will like to try a reflecting boundary random walk model that will constrain the accumulation process to be on a 0,1, as we believe that it will help the pre-intercept model in the conditions where it is doing poorly on. Thank you very much for listening to me, and I would like to exchange with you throughout the entire conference, and feel free to ask any questions you have during the Q&A. Thank you, and bye-bye.